Hi everyone, I'm really happy to be here today and thank you all for joining. I'll introduce myself. My name is Naomi. I'm a software developer with previous experience in risk and data analysis. And this lecture today, String Comparison in Real Life, is inspired by various projects that I've conducted at my workplace. One of my main goals today is to provide you tools and ideas that you can apply at your day-to-day work. Now, before we dive in and start talking about all the different methods that we will discuss today, when they're useful and why, I want to start by sharing with you a story. This is a story about me and the world of string comparison, but most of all, this is a story about why what we will discuss today is really relevant for you. So my story starts about a year and a half ago. I was at work and I noticed that one of my colleagues was quite struggling with comparing two large sets of data, or of strings to be precise. So this colleague of mine, he knew that the two sets of data he was trying to compare were very similar to one another, but not quite identical. And he wanted for each pair of strings that he was comparing to be able to determine the similarity level, or difference level if you'd like, by producing some sort of a similarity score. So he decided to come up with his own set of logics, aiming to tackle different scenarios that we face when we compare strings. Now, of course, trying to come up with your own set of logics, it's difficult, it's complicated, it is not very intuitive. But looking back at what he did, I have to say that he had a point. Because when we talk about string comparison, actually, many things would go wrong. I mean, we have typos and abbreviations, maybe the words have been reordered in the sentence, or repeated with no added value to the meaning of the sentence. Or even if we talk about punctuation, we have dot and comma and a dash and many things that could affect the result of the comparison. But most of all, bring us to one important conclusion. There is no single definition for similarity or difference of strings. So my goal is that by the end of this lecture, you will not only be familiar with the different obstacles that we face when you go to work, but you will also have a wide enough set of tools to make your next data-oriented project efficient, elegant, and useful. Because at the end of the day, when we talk about string comparison, we talk about something that has a lot of real-world applications if we only know how to use that correctly. For example, let's talk about fraud detection. Fraudsters many times steal other people's identities in order to obtain credit line and make financial purchases. Now, if we are a company working in financial services, we would probably like to know if the person on the other side of the screen is a fraudster or suspected to be one. This way, we would be able to prevent a purchase from being made or take additional security measures in order to verify the identity of the person on the other side of the screen. So let's take this a bit more to practice. Let's say that we are indeed a company working in financial services, and we have access to a list of identities that we know are commonly used by fraudsters, either stolen identities or made-up identities. And in this list of identities, we have access to the people's full names, addresses, and other relevant such identifiers. So let's look at George Forge. George is a legitimate person whose identity has been stolen and is now being used by a fraudster. The fraudster wants to open an account in our service by using the info of George. Now, as you can see, the fraudster decided to tweak a few minor details when opening the account. If we were trying to compare the info that was provided to us with the info that we already have by using only exact match, the comparison would fail. But if we would be able to use a more flexible string comparison algorithm, we would also be able to say, this looks like usage in the info of George, let's dig in a bit deeper. Another usage that I want to discuss is flexibility for typos. So let's say that we are developing a guessing game. And in our game, the user needs to guess a word or a sentence, which is practically a string, by typing in free text. So for long-life strings, we would like to have some flexibility because let's say that the user misspelled a character, maybe added one, removed one, or replaced one character with another one. So in case a human being would look at the pair of strings and would say, this practically looks like the same thing for me, we as the developers of the game would like to say, let's not reject the input. Another usage that I want to discuss is in the medtech industry. Did you know? Comparing sequences of DNA is done by comparing sets of strings. Now, we will look more in depth to this DNA sequencing example later on in this lecture. And of course, the list could go on and on. There are many different usages for string comparison. We just need to be familiar with the tools. And Python gives us some built-in operations for string comparison, but I want to briefly discuss them and see why they're not exactly what we're looking for today. First built-in operation is exact match. When using exact match, even a single change of a character, replacing it with another one or changing it to a capital letter is already enough to have the exact match returning the value false. Now, this is great for many applications, but if we're talking about edge cases, typos, a Boolean answer is not good enough for us. Another built-in operation is the ability to check if one string is contained in the other. So if one string is fully contained in the other one, this is great. But if we're talking about partial containment, typos, such different edge cases, again, this is not flexible enough for our needs. And that is when the comparison methods that we will discuss today will get into action. So today we will learn about two Python libraries. The first is called Jellyfish, and the second is called Fuzzy Wuzzy. Yeah, don't worry about the bear. We will get to it later. So, Jellyfish. Let's begin. Jellyfish is a Python library that has two main sections of functions. The first is of edit distance functions. Here, each such function receives two strings and produces a distance score by counting the amount of steps required in order to convert string A to string B. The second section is of phonetic encoding. This is not about comparison, and we will not discuss this today, but I will briefly mention that here each such function receives a string and produces a code which indicates about the phonetic pronunciation of the string. So under edit distance, we will learn about Levenshtein distance and the Levenshtein distance. But before doing so, I want to introduce a term, a definition of string metric. String metric receives two strings and produces a distance score by applying some sort of magic, as you can see. Now, both Levenshtein distance and the Levenshtein distance are different types of string metrics, each of them with a slightly different logic to calculate the distance score. Levenshtein distance is a very fundamental and important string metric in the string comparison world. Many other string metrics and string comparison algorithms are based on that one, including all the ones that we will discuss today. So Levenshtein distance counts the minimal amount of steps required in order to convert string A to string B. A step is considered as an addition of a character, a deletion of a character, or a replacement of one character in another one. The higher the score is, the bigger the difference. So let's look at a few examples to make this much more clear. In our first example, we can see a comparison between exit and exist. Here, in order to convert string A to string B, all that we would have to do would be add in the letter S. Now, going the other way around, if you would like to convert string B to string A, all that we would have to do would be removing the letter S. So in this case, no matter which direction we choose to take, the minimal amount of steps required in order to make the conversion would be 1. Now, in our second example, we can see a comparison between great and great. In this case, in order to convert string A to string B, all that we would have to do would be removing the letter E from the first string and then adding the letter E again at the end of that string. In this case, the minimal amount of steps required in order to convert string A to string B would be 2. And on our third example, we can see a comparison between look and lock. In this case, technically, in order to convert string A to string B, we could have removed the second O from the word look and then add the letter C instead, and this would result in 2 steps. But we also have the step of replacement. So we can replace the second O with C, and then the minimal amount of steps required in order to make the conversion would be 1. We will note that replacement is when we are looking at a single index and replacing for that same index one character with another one. That is why replacement only takes place on the third example and not on the second example. Because in the second example, E, the letter E was relocated from one index to another one. Now, we are moving on to the Levenshtein distance. The Levenshtein distance is very similar to Levenshtein distance, but it also has an added value. The Levenshtein distance counts the swap of 2 adjacent characters as a single step instead of 2 steps. So let's look at our next example to make this much more clear. Here we can see a comparison between swap and sup. Now the Levenshtein distance recognizes that 2 adjacent characters A and W have been swapped, and therefore It counts this as a single step. But for Levenshtein distance, we can see that this would be 2 steps, because for Levenshtein distance, in order to make the conversion, we would have to remove the letter W and then add it again, or remove the letter A and then add it again. So this would be 2 steps. Now we are getting to our most important question. When is it useful? When can we make use of that? So let's look at our next example. Here we can see DNA sequencing. DNA sequencing is the act of taking 2 sequences of DNA and comparing them in order to determine the distance level between them. DNA sequencing is commonly done by using Levenshtein distance, which is something that I, by the way, find as pretty cool. And now moving on to our next example, we can see 2 comparisons, where the first is Mr. Bean versus Mr. Bean, and the second is Johnny Depp versus Johnny Depp. In the first example, we can see that the only difference is a dot, which we, by the way, know indicates about an abbreviation. And on the second example, the only difference is a swap of 2 adjacent characters. Now, we could say that if we know our expected input is a person's full name, it is very probable that for small enough changes, maybe 1 step, 2 steps of difference, would be small enough for us to say, this is practically the same thing for me. Let's not reject the input. Now we're getting to our next question. When is it not useful? So I want to show you the next example. Here we can see I love comparing strings versus comparing strings I love. Now, if we check out the distance score, we can see that it is 14, which is quite high. Without any additional information, we would not be able to determine if the distance score is so high because the strings are indeed unrelated from one another, or if this is a case that a person, a human being, will look at a pair of strings and would say, this is practically the same thing for me. Let's not reject the input. And that is when Fuzzy Wuzzy is getting into action. Now, before we talk about Fuzzy Wuzzy, there's one thing that we have to talk about. I mean, did you know that Fuzzy Wuzzy was a bear that had no hair? So Fuzzy Wuzzy wasn't very fuzzy, was he? Now, apparently, Fuzzy Wuzzy is a rhyme or a tongue twister. And I was not familiar to that at all until I started working with Fuzzy Wuzzy Python library. So I guess there's always something new to learn. And today we will learn more about this library. So let's begin. Fuzzy Wuzzy is a library that has a few different functions. Each such function receives 2 strings and produces a similarity score on a scale of 0 to 100. 0 indicates no match. The strings are completely unrelated from one another, and 100 indicates either an exact match or something very close to that. Now today, under Fuzzy Wuzzy, we will learn about 3 functions: fuzz ratio, fuzz token sort ratio, and fuzz token set ratio. So let's start with our first function, fuzz ratio. Fuzz ratio is a function that receives 2 strings and produces a similarity score based on the following equation. Given 2 strings, where t is the total number of elements, which is practically characters, and m is the total number of matches, where matches are defined as characters that appear in both sequences and in the same order, so the similarity score is given by the equation twice, m divided by t, all multiplied by 100. Now, to give you a bit more sense, a bit more intuition about this equation, I want to show you what happens when we are comparing 2 identical strings. So here, when we are comparing same and same, we can see that m, number of matches, is 4, t, total length, is 8, and then using our equation, we would see that the similarity score is 100. And if we would be comparing 2 strings that are completely unrelated from one another, we would be able to see that m number of matches is 0, which is also our numerator. So in this case, the similarity score would also be 0. Now moving on to a more realistic example, something in between, we can see that the comparison between great and green is a comparison where m, number of matches, is 3, because G, R, and E appear in both sequences and in the same order. T, total length, is 10. Therefore, the equation gives us that twice 3 divided by 10, all multiplied by 100, is 60. Now, I want to discuss this example because I think it's a pretty interesting one. Here we can see 2 comparisons, where the first is for 2 addresses that are very similar to one another, let alone a few minor changes, and the second comparison is A versus A, B, C, D, E. Now, if we would be checking the distance score, we would see that the distance score for both comparisons is the same. It is 4. But if we would check the similarity score, we would be able to see that using fuzz ratio function, the similarity score of the first comparison is 96, which is on a scale of 0 to 100 relatively high. And the similarity score for the second comparison is 33. And here, on a scale of 0 to 100, it is relatively low. So this is interesting because now we can see the added value that fuzz ratio gives us, where the jellyfish function that we saw before could not give us. Another thing that we want to take into account when we're using fuzz ratio function is that it is case sensitive. As you can see here, capital A and non-capital A are considered as two different strings. So if we do not care about capitalization, we would want to apply lower on our strings before making the comparison. The case sensitivity is true for fuzz ratio function, but it is not true for all fuzzy-wuzzy functions. Now, when we're talking about fuzzy-wuzzy, that we know all of the fuzzy-wuzzy functions produce similarity scores on a scale of 0 to 100, we also want to be familiar with an important concept, which is called a threshold score. So let's say that we have a project, and in our project, we made 3 comparisons. The first comparison resulted a score of 90. The second comparison resulted a score of 95. And the third comparison resulted a score of 96 or 97 or 98. So we would like to ask ourselves, for which score are two given strings considered as identical or similar enough to one another? And for which score are two given strings considered as different? Now, the answer for that is a threshold score. So let's say that in our project, we decided that all comparisons with scores of 80 and above would be considered as similar, and all comparisons with scores of 30 and below would be considered as different. And all comparisons that resulted scores in the range in between would be considered as undecisive, inconclusive. So our next question now would be, how do we choose the threshold score? Now, the full answer for that is a bit more lengthy than the scope of this lecture, but I will briefly mention that it depends on the requirements and the needs of our project. For example, it is possible that in different projects we would have a higher or a lower tolerance level for what we would call as errors, maybe false positives, true negatives. So we would want to adjust our threshold scores accordingly. Also, another thing to take into account is the characteristics of the data that we are working with. For example, let's say that we have 2 different projects. In both projects, we would compare people's full names. But in one project, these would be people coming from the US. And in the second project, these would be people coming from Europe. So it is possible that in different continents, people's names would be longer, shorter, or more similar to one another. So it is also possible that same scores in different projects could indicate completely different things. Therefore, we will need to take these considerations into account when we are choosing our threshold scores. Now, let's move on to our next function, fuzz token sort ratio. Fuzz token sort ratio sorts the tokens, practically substrings, before making the comparison. So here we can see sort and compare versus compare and sort would produce a similarity score of 100. Now, moving on to a more realistic example, we can see Emma walked home with Lisa versus Lisa walked with Emma home. In this case, the similarity score would be again 100. It also teaches us that fuzz token sort ratio is not case sensitive. Now, moving on to our last function for today, fuzz token set ratio. Fuzz token set ratio is very similar to the previous function that we saw now, fuzz token sort ratio, in the meaning that it is not case sensitive and it sorts the tokens before making a comparison. But it also has the added value of a set, which means it does not count duplicates. So as you can see in our next example, sort, lower, and no repeats versus lower, no repeats, sort, and sort produces a similarity score of 100. Now, if we would take the same comparison but use the previous function, we would see that the similarity score is lower, 91 in this case, because the previous function, as we know, does not remove duplicates before making the comparison. Now, moving on to a more realistic example, we can see I love chocolate and ice cream compared to I love ice cream and I love chocolate. True story, by the way. So in this case, we can see that the similarity score is 100. Now I want to discuss the usages and advantages of fuzzy-wuzzy. Fuzzy Wuzzy produces similarity scores on a scale of 0 to 100 for pairs of strings. It also has tolerance for what we would call as typos, which is minor changes in the strings. So it is possible for two given strings that are very similar to one another and not quite identical to produce similarity score of 100. Because eventually, Fuzzy Wuzzy is here to answer the question, would a human being who looks at a pair of strings say, this practically looks like the same thing for me? And if not, so to which extent? Fuzzy Wuzzy also has tolerance for changes in order of substrings, depending on the function that we choose to use. And it also has tolerance for repetitions, again, depending on the functions that we choose to use. Another thing that we want to know about Fuzzy Wuzzy is that it simplifies the data preprocessing step for us. Because when we approach a data-oriented project, we would want to go through the data preprocessing step, which means cleaning the data before making a comparison, and therefore we would be able to increase the accuracy of our results. So if our data preprocessing step goes through removing duplicates, sorting substrings, and applying lower, we know that Fuzzy Wuzzy can do all of these things for us. Another thing that we want to know about Fuzzy Wuzzy, which is also true to the jellyfish functions that we saw before, is that it is really easy to use. So in case we have a feature or maybe a planned feature that is really nice to have, it is not top priority, not very urgent, we would want to be familiar with Fuzzy Wuzzy and jellyfish because in this case, it would not waste expensive time of our software developers, data scientists, or data analysts, because it is really easy to learn, easy to use, easy to change whenever we need. Now, if you want to know more about Fuzzy Wuzzy, I invite you to check out the articles that I wrote about it and posted on Medium. The first article covers the functions that we learned today and also covers another function that we did not discuss today. And the second article talks more about the process. It gets to the before and after of making a comparison, gets more in depth to the data preprocessing step, as well as explains what to do after we already made a comparison and have the scores with us. And now let's see what we learned today. Today we learned about two Python libraries. The first is called Jellyfish, and the second is called Fuzzy Wuzzy. Under Jellyfish, we learned about Levenshtein distance and the Mara-Levenshtein distance. And under Fuzzy Wuzzy, we learned about fuzz ratio, fuzz token sort ratio, and fuzz token set ratio. One last thing before we finish. If you have any questions, comments, or simply want to keep in touch, I invite you to reach out to me using my LinkedIn profile. Also, if you want to get more of the contents that I write, I invite you to follow me on Medium. That's it. That's all for today. Thank you all for listening, and I hope you enjoyed the lecture. I was Naomi Kriger, explaining about string comparison in real life.